Okay.
Introduce you. It's a pleasure to introduce Juan Orendain from the National University of Mexico in Mexico, who will speak to us about length one double categories via end indexing. Juan, whenever you're ready.
Okay, yeah, thank you very much, Martin. So I'd like to start off by thanking you, Martin, Doret, and Professor DeBook for organizing this. I can tell it's been a lot of work, so thank you very much. And first, thank you very much for the invitation. So the title of my talk is, yeah, as you said, length one double categories via end indexings. So this is part of a program I've been working on for a couple of years now. It started out when I was studying the Bartels, Douglas, and Henriquez version of the Stolz-Steigner program. One of their main results there was that they organized what they call coordinate-free conformal nets into asymmetric monoidal tricategory. They have a long list of long papers on this, but when I read them, one of the things that for some reason stood out was that, well, their symmetric monoidal structure had to go through a symmetric monoidal structure on the bicategory of Van algebras. And the strategy that they followed was Schulman's strategy, or the strategy that he lays out on one of his papers on defining symmetric monoidal structures on bicategories, which is to extend your bicategory to a frame bicategory, then make that into a symmetric monoidal frame bicategory, and then horizontalize your symmetric monoidal structure. And they could not define a symmetric monoidal structure on the whole bicategory of Van algebras. They could do this for a special class of Van algebras, which they called the semi-simple Van algebras. And they could not extend the whole thing to a frame bicategory. They could just do it for a certain class of vertical arrows, which were what they called finite index morphisms. So for some reason, I got interested in this, and I started to think about this problem categorically or formally. The problem was essentially the topology of binomial algebras and their representations, which is pretty ill-behaved categorically. So it turned out after a while that this was a somewhat interesting problem in its own right, and the arguments and problems had been used and thought about in other parts of the area. So in my talk, there won't be that much topology. There will just be double categories and a bunch of drawings. But I think if people in the audience know about non-commutative homotopy theory, you might recognize some of the arguments and some of the examples. And in the end, there will be some overlap in with Matthias's talk. So maybe, yeah, will be somewhat interesting. Okay, so I'll just start with some notation. So I'll be talking about double categories. So I'll be talking about squares. So I'll be using this notation here. So if C is a double category, generic square in C will be drawn like this. So I'll read squares from left to right and from top to bottom. So I think Dawson and Perret use this notation in one of their papers. So yeah, so this is easier to draw. I'll implement vertical and horizontal composition of squares as vertical and horizontal concatenation as always. I'll draw horizontal identities as red arrows, vertical identities as blue arrows. So I'll draw horizontal identities and globular squares like this. Okay, so I'll just put this problem of extending a bicategory to a double category in formal terms so that we can talk about it out loud. So yeah, the first definition is the following. So a decorated bicategory is a pair B star comma B, where B star is a category and B is a bicategory, such that the objects of B star and B are the same. So we represent a decorated bicategory as a bunch of diagrams of this form. So a bunch of vertical arrows, which are the arrows of our decoration, and a bunch of globular diagrams, which we read from left to right and top to bottom, and where the sets of vertices of the two types of diagrams are the same. So this is just the fact that this is a decorated bicategory. So our running example is the following. So if C is a double category, then the pair formed by the category of objects C0 of C and the bicategory, the horizontal bicategory of C, HC is a decorated bicategory. So we write this decorated bicategory by H star C, and we call it the decorated horizontalization of C. So the decorated horizontalization of a double category is essentially the same thing as its horizontal bicategory, just remembering the vertical arrows. So we're interested in the following problem. So given a decorated bicategory B star comma B, So we're interested in finding double category C such that the decorated horizontalization of C is our initial decorated by category B star comma B. So we call any such double category C an internalization of B star comma B. So given a decorated horizontalization, we want to find internalizations of B star comma B. So if we do this, then we're also interested in the problem of understanding the structure of the collection of internalizations of our decorated by category, of course. So we call this problem the problem of existence of internalizations. The problem of existence of internalizations then asks if the decorated horizontalization construction is generic, that is, if every decorated by category can be written as the decorated horizontalization of a given double category. So we think of the above problem, of this problem of existence of internalizations, as a problem of coherently filling hollow squares of this form, which we form with the one-dimensional data provided to us by our decorated by category. So if we have a decorated by category, we, as I said, we have vertical arrows, and we have horizontal arrows, which are the edges of our globular diagrams, and the vertices are the same. So we can form the squares here. And we want to fill this in a coherent way, that is, in a way that the fillers form a double category, and in such a way that the one-dimensional data and the globular data we started with is fixed. So problems of filling squares with globular data classically appear in many parts of the area. So, for example, in Kelly and Street's formulation of the mates correspondence, in the definition of the two-dimensional homotopy groups, and the proof of the two-dimensional Seifert-Van-Kempen theorem of Brown and Spencer, and in providing symmetric monoidal structures on bicategories via Schulman's theory of frame bicategories, as I mentioned before. So yeah, this is a problem that sort of appears in different parts of the area, not just in binomial algebras. Okay, so we're interested in this. So given a decorated by category, we want to find a double category such that its decorated horizontalization is the decorated by category we started with. So it turns out that if this problem has a solution, then we can find a minimal solution. So we can make this problem as efficient as possible. I'll talk about this a bit. So this gives rise to globularly generated categories. So if C is a double category, write gamma C for the minimal sub-double category of C, containing all the horizontal identities and all the globular squares of C. So we have the following lemma. So if C is a double category, then the decorated horizontalization of this sub-double category gamma C is equal to the decorated horizontalization of the original double category C. And if D is any sub-double category of C satisfying this equation again, that is such that its decorated horizontalization is the same as the ambient double category, then gamma C is a sub-double category of C. So if we start with a double category, then obviously C is a solution to an internalization problem. To what decorated by category? Well, to its decorated horizontalization, of course. So if we start with the double category, we already know a solution to an internalization problem. But item 1 says that if we do this, then not just C is a solution to that internalization problem, but so is this double category gamma C. And 2 says that not just that, but gamma C is the minimal solution within C. So we call gamma C the globularly generated piece of the double category C. And while we have the obvious question, can we understand these minimal solutions outside the context of the ambient double category C? So we can do this in a way. We say that a double category C is globularly generated if any of the following 3 equivalent conditions are satisfied. So 1, C is equal to its globularly generated piece. 2, C is generated as a double category by its globular squares, hence the name globularly generated. And 3, C contains no proper sub-double categories D such that the decorated horizontalization of D equals the decorated horizontalization of C. So a globularly generated double category is a double category such that it's a minimal solution to the problem of existence of internalizations that it solves. Okay, so if C is a globularly generated, so more concretely, C is a globularly generated double category if every square in C admits a subdivision, say something like this, where every smaller square is of one of these 2 forms. It's either a horizontal identity or a globular square. From this definition, it would seem that the condition is trivial. I won't talk about any examples, but yeah, it turns out that it's not trivial at all. Okay, so yeah, what I want to talk about is length. So I've talked about this program with Bob Perret quite a few times, and he's mentioned that one of his, let's say, dreams, I don't know, well, one of the things that he would like to do is to define numerical invariance on general double categories. And through the theory of globularly generated double categories, we can actually do this. So I'll explain a bit about this invariant, which I call the length. So suppose C is a globularly generated double category. We think of globular and horizontal identity squares as the simple possible squares in C. So these are the generators of C. So we draw them as squares marked with 0. We think of them as squares of complexity 0 or squares of length 0.
Sorry, is it just me who can't hear anything, or is no? It's everyone. It looks like Juan's connection is down. Oh, that's.
I think we lost Juan for a moment.
We say that a square phi in C that is of this form, and it's not of length 0. So we draw squares of length 0 as above, like this, just marked with a 1. Now, given two horizontally compatible squares phi m psi of length 1, that is, that can be written as a vertical composition of squares of length 0, it might be the case that we can find compatible length 1 presentations of phi m psi. That is, it might be the case that we can find presentations of phi m psi as vertical compositions of squares of length 0 in such a way that the squares of length 0 match horizontally in this way. So obviously, squares of length 0 are closed under horizontal composition, and in that case, well, our horizontal composition could be written as a vertical composition of squares of length 0, and then this would have length less than or equal to 1. But it turns out that this not always happen. The horizontal composition can look like this for any length 1 subdivision of phi m psi. So if we have phi m psi to horizontally compatible squares of length 1, it might be the case that for any two decompositions of phi m psi as vertical composition of squares of length 0, then the squares of length 0 don't match of phi m psi. So in that case, our horizontal composition is not of length 1, and then if that's the case, then we just write this. We say that the length of the horizontal composition is 1 plus 1/2. We then define squares of length 2 to be squares that can be written as the vertical composition of squares of length less than or equal to 1 plus 1/2, and so on. Doing the same thing, we can define inductively squares of length n for every positive integer n. So I'll just focus on squares of length 1 and length 1 plus 1/2, so I won't define length for greater integers. So, but yeah, this is essentially the idea. You have your generators, which are squares of length 0, then you consider all those squares that can be written as a vertical composition of squares of length 0, then you take horizontal composition. Sometimes these are of length 0, and sometimes these are of length 1 and sometimes not, and then you consider vertical compositions of those squares that are not of length 1, that are horizontal compositions of squares of length 1. Yeah, so, well, there's a theorem. You actually have to prove this, that the length is defined for every square on a globularly generated double category. So this is the fact that, well, this is defined through a filtration, which I call the vertical filtration of a globularly generated double category. And, well, you have to prove that this is actually a filtration. But anyways, yeah, every square in a globularly generated double category has a length. So yeah, this is an invariant for squares in a globularly generated double category. But we can extend that to an invariant of a general globularly generated double category. So if C is a globularly generated double category, then we write LC for the supremum of all the lengths of all the squares in C. And we call LC the length or the vertical length of C. So this is defined for globularly generated double categories. For general double categories, we define the vertical length or the length of a general double category as the length of its globularly generated piece. So this is well defined because of a lot of reasons, mainly the fact that globularly generated double categories is a two sub-reflective two category of general double categories. But well, so yeah, so we have an invariant for general double categories. So the intuition behind this definition is that the length measures the complexity of mixed compositions of horizontal identity and globular squares in C. So this is essentially what the length measures on a double category. So we have the following examples. So if B is any bicategory, then the length of the trivial double category associated to B is 1. The length of the quintets of a two category is 1. The length of bimodules is 1. The length of profunctors is 1. The length of spans and co-spans is 1 for any category C with pullbacks or pushouts. The length of polynomial comonoids is 1. The length of open Petri nets is 1. The length of the two homotopy double groupoid of a three-filtered topological space is 1. So we have lots of examples of double categories of length 1. So the obvious question is this length function trivial? Is the length of every double category 1? And the answer is no. There are examples of globularly generated double categories, of a sequence of globularly generated double categories Cn for every positive integer n, such that the length of Cn is n. And moreover, we can construct this sequence of double categories as a chain. Then we can take the limit. We can prove that that's globularly generated, and we can prove that the length of that is infinite. So, yeah, the length is not trivial, but we have all these examples here. Well, there's one thing in common in all these examples is that these are all frame by categories. So we have the following conjecture: if C is a frame by category, then the length of C is 1. And I'm pretty sure I can prove this. I haven't gotten around in doing it, but I'm pretty sure this is true. So we can assume this is true. So as I mentioned in the beginning, one of the motivations for doing this was to define symmetric monoidal structures on bicategories. So of course we want to extend or want to internalize decorated bicategories into frame bicategories. But knowing when a globularly generated bicategory, when a globularly generated double category is a frame bicategory, it's very difficult. So if we know that frame bicategories are of length 1, then if we have a decorated bicategory, we can try to internalize it into globularly generated double categories of length 1, and then we have a good chance that this is the globularly generated piece of a frame bicategory. So we want to have methods to internalize decorated bicategories into globularly generated double categories of length 1. Yeah, so the problem that I'm talking about today is the following. So for any decorated bicategory B star comma B, together with some unspecified extra structure that I will talk about in the end of the talk, we want to associate an internalization C of B star comma B of length 1. So this is motivated by this conjecture and by the fact that globularly generated double categories of length 1 are the ECS double categories, the ECS globularly generated double categories. Okay, well, what can we say about double categories of length 1? Suppose C is a globularly generated double category of length 1, and suppose phi m psi are squares, again, of length 1. Then if the horizontal composition of phi m psi is well defined, then this is of length less than or equal to 1. So we can actually find subdivisions of phi m psi as vertical compositions of squares of length 0 in such a way that the squares of length 0 are horizontally compatible. So again, we're starting with a decorated bicategory, and we want to associate to this a globularly generated double category of length 1. So we want to sort of use this extra data that I haven't said what it is to sort of recreate the situation here. So this is very generic, and so it's very difficult to sort of recreate this from nothing. So the strategy that we're following is that we want to construct a globularly generated double category such that every square of length 1 admits a sort of a canonical vertical subdivision into squares of complexity 0 in such a way that these canonical subdivisions are closed under horizontal composition. So we want to define a globularly generated double category in such a way that we can find decompositions like this that are canonical in some sense, have a canonical form, and this canonical form is closed under horizontal compositions, then in that case, we would have this automatically. So what exactly do I mean by canonical vertical subdivision into squares of complexity 0? Well, an example that happens in nature is the following. So if C is a globularly generated double category, suppose that every square phi of C of length 1 admits a vertical subdivision of squares into squares of complexity 0 of this form. So this is sort of like a sandwich or a hamburger or whatever, where the top and bottom buns are globular squares and the middle is, or the meat is a horizontal identity. So we assume that we have a globularly generated double category where every length 1 square can be written like this. So if that's the case, then the horizontal composition of, observe that the horizontal composition of any two squares of the above form, of this form, is again of this form. So if you take two squares of this form, then using the exchange relation, we can compose this 2 horizontally, which is again of this form. We can compose this 2 horizontally, which is of the same form, and we can compose this 2 horizontal identities horizontally, which is again of this form. So yeah, so if we have a globularly generated double category where every length 1 square can be written like this, then this globularly generated double category is automatically of length 1. And this does happen in the wild. This is actually how we prove that the length of the double category of bimodules is 1. So we actually want this. So we the canonical form that we want, or that we'll try to build, is this form here. So again, we start with a decorated bicategory. We want to build from that and some extra data, a globularly generated double internalization such that every square of length 1 admits a subdivision like this. And then in that case, the globularly generated internalization is automatically of length 1. Okay, so how do we do this? Well, we have a structure theorem or result, well, a lemma for squares of length 1 in general globularly generated double categories. So the lemma says that if C is a globularly generated double category and phi is a square in C of length 1, then phi admits a vertical subdivision like this. There's some 3 types of squares, alphas, psi, and phi's. So there's 2 alphas, the top and bottom bonds, or the globular squares, which are globular like this, and where the middle morphisms or the middle squares are either horizontal identities or globular 2 endomorphisms of red edges. So every length 1 square in a general globularly generated double category can be written as a square like this, a globular square, then a composition of squares like this, and then a final square like this. So using the structure theorem or structure result, then we want to find conditions that assure us that we can achieve this form here. Okay, now how do we do this? Now suppose that every pair of for every pair of squares phi and psi is above. So again, phi and psi are like this. So the phi's are globular 2 endomorphisms, and psi's are horizontal identities. And suppose that we have an equation like this. So if we have phi and psi, so psi is a horizontal identity and phi is a globular 2 endomorphism of a red edge, then suppose that this composition is this composition where this is another 2 endomorphism of another red edge. That is, suppose that we can slide 2 endomorphisms of red edges along horizontal identities, or pictorially suppose that we have this equation here. So we have a horizontal identity, a globular square like this, then this vertical composition is the same as a vertical composition like this, where these 2 squares are the same form, but in principle they're different. So if we can do this, then we can stack in this decomposition here, we can stack all the psi i's on the right and the phi i's on the left. The phi i's are globular 2 endomorphisms of red arrows. So we would get something like this. So the vertical composition of all of those is of this form. And then we would get a composition of a square of this form and a square of this form, which is again a square of this form. Then we would get a vertical composition of horizontal identities, which is again a horizontal identity, and a square of this form, which would be a square of this form. So, okay, that's what we want. Yeah, that's what it said. So, Okay, so essentially what we want is to recreate this relation here. So if we could do this in a good way, coherently, then we would want, of course, this to be to define. So if we fix a horizontal identity square like this, then we would want this to define a morphism from the globular monoid of globular endomorphisms of this red edge into the monoid of globular endomorphisms of this red edge. And moreover, we would like this to be functorial with respect to this morphism F. So finally, so yeah, with all this, we can reconstruct what we want. So what we want is the following. So if B star comma B is a decorated by category, then an end indexing of the decoration B star with respect to the decorated by category B star comma B is a functor phi from B star to the two category of categories functors to natural transformation, such that for every object A and B star, the category associated to this object is the looping category of the monoid of endomorphisms of the red edge associated to A. Well, I wrote here functor, but this works in a pseudo setting as well. So this is an end indexing. So this is essentially putting a formal name to this argument here. An example of an end indexing, which is a toy, very baby version of what Matthias talked about before. So if G is a group, A is an abelian group, then the looping of G and the double D-looping of A. So the double D-looping is a two groupoid with a single object and single horizontal one morphism, and where the two endomorphisms are A. So this is a decorated by category. So here the so the end indexings of omega G with respect to omega G comma omega squared G is equal to the category, or these are the actions of G on A. So if this is pseudo here, these are the actions twisted by a co-cycle. Okay, so I didn't write this, I'm sorry. So we'll write end cat B star comma B like this for the category of end indexings of a category B star with respect to a decorated by category B star comma B. Now, if B star comma B is a decorated by category, then we write G cat B star comma B L1 for the category of globularly generated double category C, such that H star C B star is equal to B star comma B, and such that the length of C equals 1. So this is the category of globularly generated internalizations of B star comma B of length 1. So our main theorem says the following. So if B star comma B is a decorated by category, then there exists an embedding of category C from this category of end indexings of B star with respect to B star comma B into this category of globularly generated internalizations of B star comma B of length 1. So given an end indexing phi of B star with respect to B star comma B, that is an element here, an object here, the category of horizontal endomorphism squares the image of this indexing here under this embedding here. The category of horizontal endomorphisms is actually the Roughan deconstruction. So, yeah.
When you have just one more minute.
Okay. Well, so this restricts in the toy version, in the toy case that I mentioned, to cross products, and well, I have some questions and conjectures. So essentially, well, we have defined a length, sort of an invariant of general double categories. What formal properties does this invariant satisfy? Can we categorify this invariant? We want to study this invariant in the sense of general invariants for double categories. And well, there's some other questions, maybe not as interesting. So what's the relationship between this construction that I just mentioned and the construction of frame by categories through monoidal fibrations by Schulman? And yeah, I don't know, there are some interesting questions that I'd be very happy to talk about afterwards with anyone interested. So these are some references, and yeah, thank you very much.
All right, let's thank Juan for the talk. Yes, it is unfortunate that we don't have time for questions now, because it's already 2:31 p.m. So we'll keep the questions for the forum, if you have any, or for the breakout room in the end. So because we have 30 minutes blocks, and so that's why we were aiming for 20 minutes talks and 10 minutes for questions. All right, so let me then, Eduardo, can you hear me just fine? Are you sharing your screen?
Yeah, I can hear you. Can you hear me?
Yes.
Okay.